In this video, we're going to look at the rate of our decay, so nuclear decay rates. So essentially, we're going to look at the kinetics of our reaction. And nuclear decay does follow first-order kinetics. So if we were to look at our rate, it's going to be equal to K. Remember, lowercase k is our rate constant, so be careful to make it lowercase. Remember, capital K's were our equilibrium constants. Because it's a first order reaction, my units are going to be some unit of time raised to the -1. So 1 over time, right? Per second, per minute, per hour, per year, whatever it happens to be, but it's going to be 1 over time, or time to the -1. And then how we would have written it before, we just would have done like concentration of one thing. Here I'm going to put an N, and an N is going to represent the number of radioactive nuclei. So our rate is proportional to the number of radioactive nuclei, which is what N is representing here. And then again, it's raised to just the first power, right? If I had a 2 here, it would be second order, because if I was to double the concentration of N, my rate would go up by 4, right? If there was a 2 here. But here it's just straight proportional. If I was to double this, my rate gets doubled. If I was to cut this in half, my rate gets cut in half, right? If I was to increase this by 100, my rate goes up by 100. So my rate is proportional to the number of radioactive nuclei. It's going to follow first order kinetics. And we are going to use our integrated rate law. So you guys are getting a little review here from chapter 12. And our first, right, the integrated rate law for a first order reaction, we had the natural log, and then it was over our concentration at time t. Here I'm going to use the number of radioactive nuclei at time t, over N naught, right, my initial amount, equal to negative K, again, make sure it's lowercase, times t, which is time. So N naught is my initial amount. If we were solving for a percent, it would be 100%, right? It's how much I'm starting out with. And T is the amount that remains at time T, not the amount that has reacted, but the amount that remains. And then, of course, T is time and K is my rate constant. The number of radioactive nuclei are proportional to mass, so a lot of times we just use mass instead of amount. So the number of nuclei is proportional to its mass. So often mass is used instead. So usually instead of plugging in an amount, we're going to plug in the mass, and that's fine. If we were to look at the half-life, remember the half-life for a first order reaction was constant, right? It doesn't change. So our first half-life is the same as our second half-life, which is the same as our third half-life, right? It was the natural log of 2 over our rate constant, lowercase k, which if we were to work out the natural log of 2 and round it to 3 significant digits, it comes out to 0.693 over K. So basically it's constant, right? I have a number on top and a constant on the bottom. It doesn't change. So it's constant for first order reactions. And our radioactive decay rates are always going to be first order, so it's always going to be constant. And we should write half-life as constant. So the half-life is constant for first order reactions. So for our nuclear reactions, it will be constant, right? Each consecutive half-life is the same amount of time. So if I started out with 100 grams, the time that it took to go to 50 grams is the same amount of time that it takes to go to 25, and so on. So let's look at a couple examples here. So our first one, the radioactive decay of thallium-206 has a half-life of 4.20 minutes. And we're going to determine how many grams are left after 60 minutes if we begin with 0.250 grams of thallium-206. So we're essentially solving for NT, right? We go back up to our equation, we have N naught, right? That's the amount that I started out with, so 0.250 grams. My time is 60 minutes. We're solving for NT. My problem right now is I also don't have my rate constant. We do, however, have our half-life, so we can use this equation, right, to solve for K. Once I get K, I can plug it back into this equation. Now I only have one unknown. So essentially the first thing we need to do is determine our rate constant. So we're going to use the half-life to find our rate constant. So I know that my half-life is 4.20 minutes, and that's equal to 0.693, right, the natural log of 2 over K. So grabbing my calculator and solving for my rate constant. And I got my rate constant to be 0.165 minutes to the -1, right? I'm taking 0.693 and dividing by 4.20 minutes. My units are 1 over minute. Remember, our units on a first order rate constant are always per time. Now that I have my rate constant, we can plug it into this equation. So I'm just going to copy this, just so we have it here. So I'm going to have the natural log of my unknown, that's what we're solving for, over 0.250 grams. And then again, mathematically, remember this is the natural log of that fraction. And then that's going to be equal to -K multiplied by my time, which is 60 minutes. We go back up here to the problem. And then mathematically, these units are going to cancel, right? Minutes times 1 over minutes go away. And then what I'm going to do is I'm going to get this number. Once I have that number, I'm going to need to raise e to it because we're going to need to undo the natural log. Once I do that, we can multiply it by 0.250. So if you guys want to grab your calculators, if you haven't already, that would be a good idea. See if you get the same number as me. And I ended up with 1.25 times 10 to the -5th grams. We do want to make sure that our number is smaller than we started out with, which it is. We don't know for sure that it's right, but if I got a number that was larger than 0.250, I would know for sure that I'm wrong, right? It decreases over time, not increases. Let's do one more example. So this time I'm going to have carbon 14. And it decays by beta emission and has a half-life of 5,730 years. This is the isotope that they use when they do carbon dating. So if you've heard of carbon dating before, it's this reaction. So we're going to write the balanced equation. You have seen this one before, don't look back in your notes. And second one, we're going to determine the percentage of carbon 14 that remains. After 3,310 years. So I would like you to try this one on your own. So again, please just hit pause, work through the problem, and then when you're ready to check your work, hit play again. Alrighty, so hopefully you guys did that. So carbon 14, I have an atomic number of 6, and it's decaying by emitting a beta particle. And this was our symbol for our beta particle. If you use this version, that's absolutely fine. And then balancing it, because I have a 6 here and a -1 here, I know that this needs to be a 7, right? 7 plus a -1 is going to give me a 6. I also know that when I undergo beta emission, I'm actually taking a neutron and changing it into a proton, so my atomic number does increase. This is going to be a 0, and then looking on the periodic table, oops, sorry, not a 0. I'm adding 0, it's going to be a 14. That'd be crazy if it was a 0. And then looking on the periodic table, I'm going to have nitrogen. So my balanced equation. And then B, we're just going to use this formula again. I don't know K. K is unknown at this point, right? My rate constant, but I do have my half-life. Anytime I have my half-life, we can solve for K, just like we did in the previous problem, right? It's constant. So if we have a half-life, we know our rate constant. Once I get that, we have our time that's given to us in the problem. And then what I'm solving for is essentially this ratio, right? If I want the percentage that remains, N is the amount that remains. This is the amount that I started out with. So I'm going to solve for this ratio and then multiply it by 100 to get it to be a percent. So let's solve for K first. I know that my half-life is equal to 0.693 over K. So my half-life is 5,730 years. I'm determined to write 0.693 wrong every single time. And then solving for that rate constant. So I'm grabbing my calculator here. And I got 1.21 times 10 to the negative 4 years to the negative 1, right? 1 over years. Now that I have my rate constant, we'll plug that in. Again, we're solving for this fraction. And my time, 3,310 years. Years are going to cancel. So grabbing my calculator here. Don't forget to take the anti-natural log. You'll raise e to your number, and I get 0.670. And then again, we want a percent, so I'm just going to multiply it by 100. So 67.0% of it remains after 3,310 years.